SwayamPrabha. Digital India. Educated India.
Hello everyone. So let's continue to work out some more problems. This is problem number 7. Here, if UT is a zero mean, statistically stationary, differentiable, random process with autocovariance R of S and autocorrelation function rho of S, show that first part is U of t and U dot of t, as in U dot of t is d dt of ut, are uncorrelated. All right. So keep in mind, so the second part is u of t and u double dot of t, which is a second derivative in time of u of t, are negatively correlated. That's also something you have to show. Note that any two functions a of t and b of t are negatively correlated, positively correlated and uncorrelated if the covariance of AB is less than 0, greater than 0 and equal to 0 respectively, right? So if the covariance of AB is less than 0, it is negatively correlated. If it is a covariance of AB is greater than 0, it is positively correlated, and covariance of AB is equal to 0, it is uncorrelated. So let's see how to work this out. Let's look at part 1. Okay, so this is the first part. Now what we have is we need to find out the covariance of u of t. So if I go back here, it is u of t and u dot of t, isn't it? So that would be, so we need to find out the covariance of that. So that would be u of t multiplied by u dot of t, covariance of that, isn't it? So that is the same as u of t, now d dt of u of t. Covariance, close, isn't it? Now here, let's see what happens. One of the things we can do is we can commute, right? We can commute the differential operator outside. In that case, this would be d dt of u of t squared over 2, isn't it? Close covariance. That's what you have. So essentially what I'm doing is I'm taking the u of t inside this time derivative and then I'm writing it as u of t squared divided by 2. So I have d dt of u of t squared divided by 2 and then obviously the covariance of all of that. Now when you're taking a covariance, the d dt can be taken out, the time derivative can be taken out. So then what you have is d dt of u of t squared divided by 2, isn't it? So half u of t squared divided by 2. Okay, so half u of t, so d dt of half u of t squared divided by 2. Here, remember what happened here. I took the u of t inside and then I have u of t, d dt of u of t squared divided by 2. That's essentially the time derivative of the variance, isn't it? That's essentially the time derivative of the variance, half of the variance, of course. And however, what we have done is we have taken the d dt out of that covariance part, out of the time averaging part, because it is independent of that, right? So what happens is the mean and the differentiation are commuting. Okay, the mean and the differentiation are commuting. So what you're doing is you are taking the derivative of the mean instead of taking the mean of the derivative. You are commuting, right? So from this process to this process, what happened was a commuting. And then what you have is d dt of the mean of u of t squared by 2, which is essentially the d dt of half of the variance, isn't it? It is d dt of half of the variance. Now remember what this problem is. It is a statistically stationary process. That means all statistics are independent of time. They are not changing with respect to time. So essentially, this is going to be a constant with respect to time because it is statistically stationary, isn't it? Because of statistical stationarity. Statistical stationarity. That means this becomes equal to 0. So that way you have proved the first part, which is u of t times u dot of t is uncorrelated because u of t and u dot of t are uncorrelated because the average of u of t and u dot of t, as in the covariance of that, is equal to 0. Okay, now let's go to the second part. Okay, the second part is u of t and u double dot of t. Okay, so I'll do one more page here, write it in a blank page, and I want to find out the covariance of u of t and u double dot of t. So that would be the covariance of u of t times d squared dt squared of u of t, isn't it? Okay, so now I have a double derivative. I will use the chain rule and write this as d dt of u of t dut dt, isn't it? d dt of u of t dut dt minus, then what will I have? I will have dut dt and then again dut dt. Close average. Isn't it? I have used the chain rule, and instead of writing it as a double derivative, I have now written it as d dt of both of these functions minus, because if you use the chain rule, you are going to get first times the derivative of the second, which is what this term is, minus plus this second one times the derivative of the first, which is what this is. That's why I have a minus here. Okay, we have done this multiple times in other problems. Now, here is what happens. This right here, okay, d dt, I can commute the differential operator, and then what I have is u of t dut, d dt of u of t. Isn't it? That's your first term. Minus dut dt and dut dt. Isn't it? I just split, I took the averaging of the first term and the second term separately. Now look at what this is. It is the covariance of u of t times u dot, isn't it? This is essentially d dt of u of t u dot of t. Okay, minus whatever this term is. This right here, u of t and u dot of t is uncorrelated as proved in the first part. So this is going to be equal to 0 minus, here you have u dot of t squared average. Isn't it? U dot of t squared average. So what you have is minus average u dot of t squared. Isn't it? This right here is a positive number, and you have negative of that, so this whole thing is going to be less than 0. Because you're taking u dot t squared, as in the derivative of u, and then you're squaring it. So it's going to be a positive number because you're taking the square. The negative of that will be a negative number, so essentially you have it less than 0, isn't it? So there you go. So the second one we have proved it like that. We had to prove that this was negatively uncorrelated, and we just did that, right? Negatively correlated. The previous one was uncorrelated, which we proved. I hope that is clear. Let's try another problem. Problem number 8. Each of the following equations is incorrect. Explain why. All right. So the first part of that is ui uj. Okay. So I am going to write this down. So first part is ui uj. What is ui uj? ui uj is what? It is the Reynolds stress, isn't it? Which is given as 0.5, 0.1, 0, 0.1, 0.3, 0.1 and 0, 0.1 and minus 0.1. This is the Reynolds stress that is given. Okay. Something is wrong in the way the Reynolds stress is given here. What could be it? So, the Reynolds stress tensor is, obviously it is going to be symmetric and it is going to be positive semi-definite, which means diagonal components u1 squared average, u2 squared average and u3 squared average, those have to be all greater than 0. So now you can easily identify, because u3 squared average seems to be less than 0. This is wrong. This cannot be the case. Right here is your culprit. Minus 0.1. That cannot be the case. So that's your mistake. So Reynolds stress in that is the mistake in the way the Reynolds stress is written, tensor is written here. Let's look at the second one. So what is given is Bij is equal to ui uj divided by ul dummy index, right, minus 1/3 delta ij, and this is equal to minus 0.4, 0.1, 0.20 and 0.1, 0 and 0.2. That is what is given here. Okay, so this is Bij, which is the Reynolds stress tensor normalized with twice the kinetic energy, essentially, right? ul is twice the kinetic energy. So, and then subtracted with minus 1/3 delta ij. So that is the Kronecker delta. Essentially what you're getting is the anisotropic part, isn't it? Now, remember, the diagonal components have to be positive, they have to be non-negative, which means the diagonal components of Bij, okay, the diagonal components of Bij have to be greater than what? What is the minimum value that this should have? The minimum, as in the minimum value that Bij should have. The minimum value that Bij should have would depend on the fact that this would be what? This would be 0, right? If that is 0, that is when you have the minimum value. And then the minimum value would be minus 1/3 would be the minimum value. So Bij has to be greater than minus 1/3. And what you have here is your B11 is equal to minus 0.4, which is less than minus 1/3. Minus 1/3 or so I should say negative 0.33. So here you are getting minus 0.4, which is less than minus 1/3. So that means that right there is your culprit. So that is the mistake there in terms of Bij. I hope that is clear. Let's try the next problem. The covariance in wave number space is defined as Rij of kappa is ui hat star of kappa and uj hat of kappa, which is basically ui hat of minus kappa, because this right here is the conjugate, and so that is ui hat of minus kappa times uj hat of kappa. Okay. Now the first part is you have to show that Rij hat is of kappa is greater than 0. Rij is basically the covariance, right? Is greater than 0 for I is equal to j, that is Rii of kappa is greater than or equal to 0. Okay. Now let's see how to do that. So the first part is pretty straightforward. If I look at the first part, so if I use the definition of Rij of kappa and then with I is equal to j, then what I get is R. What will happen is I'll have I of kappa, which would be equal to obviously covariance of ui hat star of kappa comma t times ui hat of kappa comma t. Covariance close. Think about this. This is ui star as in conjugate times itself. So a complex variable times its conjugate, that is going to give you its magnitude, which is going to be greater than or equal to 0. This right here is the magnitude. What you're getting is kinetic energy, which is going to be positive. Okay. In terms of velocity, what you're getting is kinetic energy. So if this was velocity, but for any variable, a complex number times its conjugate is going to be the magnitude. So this is going to be a number that is greater than equal to 0. Hence proved. Okay. That's your first part. Now let's go back to the second part and look at the question. From conjugate symmetry, show that Rij of kappa, Rij hat of kappa is the same as Rji hat of minus kappa, which is Rji star of kappa. Okay. So let us see how to do that. Now what I'll do is I'll start with Rji of minus kappa. Okay, Rji hat of minus kappa. Then what will I have? I will have Rji hat, of course, of minus kappa is equal to, now I'm going to use the definition of Rij. I'm going to use the definition that was given in the problem of Rij. And using the definition, this just becomes, obviously covariance open, uj star of minus kappa, because you are taking it as minus kappa, isn't it? So uj star of minus kappa comma t hat, of course, times ui hat of minus kappa comma t, isn't it? Which is what this is, this right here, except I had a minus kappa here, so I had to put a minus everywhere. Okay, so then this is what I have, right? So this becomes what? This becomes uj star of minus kappa becomes uj of kappa, uj hat of kappa comma t, and then ui hat of minus kappa becomes ui star of kappa comma t, isn't it? The minus kappa just becomes the conjugate. Because of the minus kappa, it just becomes a conjugate. Okay, this is the same as what is given here. It's the same as what is given here. So that means this just becomes Rij of kappa. So essentially what we have done is we have just shown conjugate symmetry, right? We have just shown conjugate symmetry. So Rij of kappa is Rji of minus kappa. We started with Rji of minus kappa and we proved that it is Rij of kappa. That is what it is. Okay. Now the second part, okay, in order to show the second part here, as in this one here, in the second part of the question, we have to show that it is equal to Rgi star of kappa. Here is what we do. So you start with Rji star of kappa. Okay. Then what do we get? We get Rji star of kappa is equal to covariance open. You will have, by definition, you will have Uj star of kappa comma t hat and Ui hat of kappa comma t, covariance close, and star of the whole thing because it is Rji star. Alright, it is Rji star. Then what happens is you can just take star of the whole thing, right? So conjugate of a conjugate gets you the original. So Uj of kappa comma t, Uj hat of kappa comma t, and then Ui hat of the conjugate of Ui hat becomes Ui hat star of kappa comma t. Covariance close. This right here is again by definition this one. So that would be Rij of kappa. Hence proved. That's your second. That's the entire second part of the question. We proved the first equation right here and the second equation right here. Is this clear? I hope this is clear here. Let's move on to the third part of the question. Isn't it? We have to show from the incompressibility condition. We have to show from the incompressibility condition that kappa dot u hat of kappa is equal to 0. Okay, the incompressible show that kappa I Rij of kappa is equal to kappa j Rij of kappa is equal to 0. Okay, let's see how to work it out. Now kappa I Rij hat of kappa. This is what I have to show, right? Kappa I Rij hat of kappa. That is going to be equal to, I can just use the definition of Rij of kappa. So kappa I, covariance open, Ui star of kappa comma t, right? Ui star of kappa comma t, and then Uj hat of kappa comma t. Covariance close. If I take kappa I inside, what I have is kappa I Ui star of kappa comma t, and then I will have Uj hat of kappa comma t. Right? Now this is the conjugate, so this becomes kappa I of Ui hat of minus kappa comma t, isn't it, by definition of the conjugate, and then Uj hat of kappa comma t. Okay, now here is what I do. I use a minus, okay, I put a minus outside and take a another additional minus into it. So I'll have minus kappa I Ui hat of minus kappa comma t, Uj hat of kappa comma t. Okay, look at what I have done. I have taken minus kappa I Ui. Okay, now all I need to do is replace minus kappa with kappa dash, some new kappa, right? And if I use the conjugate symmetry, right? What was the conjugate symmetry? The conjugate symmetry was Rij of minus kappa is equal to Rij of kappa. So, and if I use the conjugate symmetry, then replace kappa with kappa prime and using conjugate symmetry, from 2, what do I get? I get this, okay? I get kappa I Rij hat of kappa would be equal to minus of, okay, here is what happens. I will have kappa I prime because I'm replacing minus kappa with kappa prime. So it's a new wave number, that's all. So then I'll have ui hat of kappa prime comma t, and then uj. Now what is happening is I'm replacing kappa with minus kappa. So on the right side, sorry, the right part of this term, that also becomes minus kappa, and instead of writing it as minus kappa, I'm going to write it as uj star of kappa prime comma t close average. This right here is equal to 0 because of the incompressibility. So this becomes equal to 0. That is how I prove it. So I hope this is clear. Now there was an additional part to it where I had to prove Kij, kappa j, r hat of ij of kappa is also equal to 0. So how do I prove that? Similarly, what I do is I do kappa j rij hat of kappa, which is kappa j, right? Using the definition, it is ui star of kappa comma t and uj hat of kappa comma t. Taking the kappa j inside, I will have kappa j ui star kappa comma t uj hat of kappa comma t close covariance. And what I do is I'll just take what I'll have is I'll group the kappa j along with uj. So then what I'll have is this is star, by the way. So ui hat star of kappa comma t and then kappa j uj hat of kappa comma t. I just grouped this, that's all. I just moved it, shifted it to the left. Now this is going to be equal to 0 again because of incompressibility. So that would mean that this is equal to 0, hence proved. So what I've done is I've taken each part and proved it to be equal to 0. Isn't that what I had to do, right? Okay, so I hope you found this interesting. I hope you found this helpful, and I hope you understood it. We have a few more problems to work out, which we'll work out in the next class. Thank you.